आज सॉफ्टवेयर क्वालिटी एश्योरेंस का 22nd लेक्चर है और आज हम पिछले 21 लेक्चर्स का एक रिव्यू करेंगे. As you can appreciate that it is very difficult to go through everything that we have covered in the last 21 lecture. In the last 21 lectures in just one lecture today. But what we will do is we will try to go through topics that we have discussed in quite a bit of detail in the last 21 sittings. So let's start off with what software quality is. Quality as it relates to all aspects of software, whether they are requirements or design, code or tests, documentation or training. By now you are convinced that it is difficult to define software quality. It is somewhat like the concept of beauty. Each of us has a strong opinion about what constitutes beauty. And we recognize it when we see it, but when someone asks us to explain, it is very difficult to do so. But we can define certain characteristics of what quality is and what quality isn't. And that's what we had tried to do in this semester, in this course. But we had also looked at certain definitions from different perspectives of what software quality is. And now I would like to review them with you. First of all, and that is from the developer's perspective, from the perspective of the product, that we would want to have low levels of defects when deployed, when the product is deployed, ideally approaching to zero. And we also know that in real applications where complexity and size of the application matter, having no defects in software products is almost impossible. But in toy type, simple demo applications, we can eliminate all defects. Second is high reliability, or the capability of running without crashes or strange results. And that is a perspective from the user. But it is dependent very much on the number of defects it has and the severity of these defects. If the defects are severe and the number of defects is high, the reliability of that software product would be low. Also, we can look at quality from user's perspective, at how satisfied a user is with the product. So we can say that a majority of clients with high user satisfaction when surveyed is also point of view to look at when we are talking about software quality. Ultimately, it is the user who defines quality. And if a customer and a user is happy with the software product, then that can be the ultimate goal of the developer, that the customer is happy and satisfied. We can also define quality as a structure that can minimize bad fixes or insertion of new defects during repairs. And we have had a good discussion on this topic throughout the course. And this is also the internal view of the software, the technical view, so to speak, of the software. But this internal view has external implications, that if defects are introduced when repairs are being made, then ultimately the user of the software product will suffer, because those defects will emerge as new defects in the software product. And so quality will suffer and the user will be unhappy. Another point of view that is from the user's perspective is that the developer is providing effective customer support when problems occur. And as you know, that in all complex software systems, problems do occur. And so if you look at from the support perspective, from the perspective of the user who is out there in the field trying to use the software, if problems occur, how quickly can the development organization respond to them? And once the defects have been identified, how rapidly those defects can be repaired, especially for high severity defects. And so these 2 points that we have just discussed are a user's perspective on quality. By now, I'm sure you are convinced of why we need to have high quality software products, or why we need to have high quality in software products. Because it reduces time to market for new products, because it enhances market share compared to direct competitors. High quality software products minimize scrap and rework expenses. And we have seen that throughout the semester, that we have discussed the situations, the scenarios, and evidence that in fact the scrap and rework expenses are reduced, in some cases eliminated. The ancillary benefit of having high quality software products and working on high quality software products is that it attracts best of the class IT specialists or computer scientists. High quality software products also minimize the risk of serious litigation in cases of breach of contract. With high quality software, we minimize the risk of serious operating losses and operating failures because the software is highly reliable. We have minimal interruption in the execution of the software. And on the financial side, software quality minimizes the risk of bankruptcy or business failures, which may be attributed directly to poor quality or poor quality software products. And throughout this course, we have seen evidence that these things are true, and we do need high quality software products. When we were talking about software quality, we said that low levels of defects, ideally approaching zero when a software product is deployed, is a definition of software quality. What is a software defect? A software defect is an error or a flaw or a mistake, failure in a software that prevents it from behaving as intended, that it results in producing incorrect or unexpected result. Software defects are also known as errors, or most commonly they are known as software bugs or simply bugs. All of these terms are interchangeable. These bugs can have a wide variety of effects with varying levels of inconvenience to the user of the software. Some bugs have only a subtle effect on a program's functionality. Some of these are like cosmetic defects or cosmetic bugs. And some of them may cause serious damages. They may crash the system. They may lead to denial of service type of situations where many websites, have suffered because of this. And so the consequences of software defects range from annoyance to catastrophes. Some of them can be classified as security bugs and might, for example, enable a malicious user to bypass access controls in order to obtain unauthorized privileges. And that in itself can lead to serious damages, which can be both in terms of financial, national security, or even health, or even loss of life. As I said, the loss can be catastrophic. We talked about Ariane 5 rocket that was destroyed after less than a minute after it was launched. That was in 1996. The loss of financials was $1 billion. It was a prototype rocket that was launched by the European Space Agency, and it contained software defect in the onboard guidance computer program. And so $1 billion were lost in less than 1 minute because of the software defect. And years of work and the impact on the personnel is another thing that has not yet been counted. Similarly, there are other many problems that can be attributed to software defects. And if we don't check the growth of, let's say, viruses, these are also take root or attack our systems because we have defects in our softwares. This amount is going to increase in the future. What kinds of, or what are the categories of software defects? We talked about 4 kinds of software defects. We talked about errors of commission. We talked about errors of omission. We talked about errors of clarity and ambiguity. And we also talked about errors of speed and capacity. The errors of commission are those that are mistakes, things done wrong. Errors of omissions mean that we have left out certain things. And this is a fairly common type of defects in requirements and designs. Errors of clarity and ambiguity, again, things are not clear. Mostly these errors occur in requirements and sometimes in designs. Lastly, we have errors of speed and capacity. These errors deal with the performance and the storage requirements. And if you carefully look at all the different work products that are produced in software engineering life cycle, all 4 of them are found in almost all work products. Some of them are more amenable to some work products, like requirements documents suffer from errors of omission and errors of clarity and ambiguity. And software code typically suffer from errors of commission. And so each work product has its own favorite set of errors, I would say. But all of them can be found in almost all the work products. And each one has a difficulty in detecting and fixing. Where do these errors get into? So that is, what are the software defect origins that we have talked about. I'm just going to mention them here because we had a good discussion on them when we were talking about in the earlier part of this course. So we can have errors in requirements, we can have errors in design, errors in source code, errors in user documentation, errors due to bad fixes, errors in tables and data, and errors in test cases. All of these are the origins where these errors can get into these work products. How do we get rid of these software defects is very important. We have to devise software defect elimination strategies. These strategies, we have discussed some of them already in quite a bit of detail. Here I'm going to just go through the list. These strategies include effective defect prevention, high levels of defect removal efficiency. That is, we need to remove software defects with high efficiency. We need to be able to accurately predict defects before the project begins. This even is more difficult than the first two. We need to accurately track defects during the project lifecycle. That's where it was introduced, how it was detected, when it was fixed, and what are some of the reasons for these defects. And then we need to collect useful quality measurements and ensuring high levels of user satisfaction. These are the elements that software defect elimination strategies have. We have covered some of them, and we will cover some of them in the later part of the course. Let's now first talk about defect prevention and removal. Both defect prevention and defect removal techniques are used by the best-in-the-class companies. There are the companies which are leaders in software development and quality assurance. Defect prevention is very difficult to understand, study, and quantify. We have had some discussion on defect prevention. As far as defect removal is concerned, defect removal techniques can be classified primarily in two ways. Number one, testing techniques, and number two, non-testing techniques. What is the philosophy of defect prevention? Now let's say what defect prevention is first. Defect prevention is that we try our level best that the defects don't enter the work product, whether they are requirements or design or code or any other work product. And as I've just said, the defect prevention is a difficult concept to understand. Let's now talk about the philosophy of defect prevention. If human misconceptions are the error source, education and training can help us in removing those error sources. So what we are trying to do is that we are trying to eliminate defects within their sources. If imprecise designs and implementations that deviate from the work product specifications or design intentions are the causes of faults, then formal methods can help us prevent such deviations. And we have had a good discussion on these two topics already. If non-conformance to selected processes or standards is the problem that leads to fault injections, then process conformance or standard enforcements can help us in preventing those types of defects to appear in the work product. If certain tools or technologies can reduce fault injections, then we should use them and they should be adopted. And we have had a good discussion when we talked about the importance of integrated development environments, because these tools really help us in preventing many defects. As I've just said, that typically defect removal techniques are of two types. One are those that are testing techniques, the others are non-testing techniques. And primarily, non-testing techniques are some forms of reviews or inspections. We have had many lectures on software inspections. Inspections are a direct fault detection and removal. That is, we review the work product to directly try to find where defects are and then we remove them. On the other hand, testing is an observation of failure and then fault removal. The observation of failure is done by executing software tests, by running the programs and testing them, and if a failure occurs, then we try to locate the cause and try to eliminate the defect. These are primarily two types of defect removal techniques. We have had a good discussion on inspections, and when you come after the midterm, we'll talk about software testing. Now, what are the root causes of poor software quality? Inadequate training of managers and personnel, inadequate defect and cost measurement, and we also have a reality in software engineering, and that is excessive schedule pressure. Then we have inefficient defect removal, high complexity levels in the application domain, and ambiguous and creeping requirements and designs. These are the root causes of poor software, and during our discussions on them, we have had a good discussion on them. Let's now talk about some quality attributes. Quality attribute set is a way to represent customer quality requirements. You need to ask your current and prospective customers about their definition of quality, and you need to develop a quality program. Typically, there are two categories of quality attributes: product-specific quality attributes and organization-specific quality attributes. Let's briefly mention product-specific quality metrics here. Ease of use would be one of them. Documentation is one of them. Defect tolerance, how much tolerance can the user show with respect to the software product, with respect to the defect in software. Defect frequency, defect impact, price versus reliability, and performance. On the other hand, the organization-specific attributes include service and support and internal processes. And you can see that all of these attributes relate to the 6 quality definitions that we had talked about in the very first lecture and also reviewed them today. So any organization which is interested in having a good quality assurance program must take the input from the users and customers and develop their program based on that, and try to continuously improve the quality assurance of their work product. In order for them to have a quality program, an organization must have an SQA group. This group must be funded properly, and management must pay attention to the reports and presentations made by the group so that they can independently report to the top management. This group reports directly to the top management and not to the project management. The personnel of the SQA group must work together with the project management personnel to produce high quality software for the company, which is the ultimate goal. The development work will obviously be done by the project management staff, and the SQA group will be a watchdog group on the project, on the activities related to quality assurance. The activities of SQA group include preparation of an SQA plan for the project, participation in the development of the project software process description, and review of software engineering activities to verify compliance with the defined software process. And in case where the deviations are necessary because of certain elements, because of certain environmental constraints, or because of certain urgent situations, those deviations should be recorded and documented properly. The SQA group is also responsible to audit the design software work product to verify compliance with the activities in the software process. And so the SQA group has to work hand in hand with the project management team, with the technical staff, so that both teams can develop software which is of high quality, with which the customer is happy, and ultimately it is going to bring financial benefits to the organization. We briefly mentioned SQA plan, but we are going to discuss SQA plan in quite a bit of detail in a later lecture. We also talked about costs related to software quality. With, like everything else in life, there is cost of implementing the quality assurance activities, the techniques, the tools, the trainings, and the awareness necessary for software quality assurance. But economics of software quality assurance tells us that these costs will be paid, returned with a lot of benefit, and if invested properly, these costs will recover themselves, and the rate of investment, return on investment, will be very good. The economics, if you look at the economic side, the high quality software applications have shorter development schedules than low quality software, and as a result those products can be marketed in shorter time. High quality software applications have lower development and maintenance cost as compared to low quality applications, and this is also good from the financials perspective. High quality software applications have better reliability levels, and as a result the customer is happy. As a result, the time and money spent on trying to find defects and fixing and repairing defects when the software is being used by the customer are all not spent, and so quality is actually saving the organization money. High quality software projects score better on employee morale surveys than low quality software projects. As you are well aware that nobody wants to work on poor quality projects, or they don't want to be creating poor quality products if they are professionals. High quality software benefits or augments the performance levels of users, while poor quality software tends to degrade worker performance, and that is also a fact, and we have seen enough data that putting high quality software, putting those activities in practice which result in high quality software actually improve the productivity of the software professionals. And poor quality software applications can trigger massively unplanned expenses, and that can ultimately result in litigation or operational failures and other bad things. And so it is, from the economics perspective, it is a wise decision to invest in those areas which improves the quality of the software. We also talked about quality measurement categories, and we said that we have two types of measurements. Measurements for defects or bugs in software, and then we have measurements in user satisfaction levels. We said that we should apply or measure 100% of software projects to measure defects or bugs. But as far as the user satisfaction levels are concerned, only for software projects where clients can be queried and actually use the software consciously, so that we do not receive negative feedback. So when we are measuring, we have to be very careful. That was the introductory part of the software quality assurance course. Then we entered into the second phase, and that was the activities of the software development and quality assurance. We talked in detail about requirements in software quality assurance. We talked about different kinds of requirements, including functional, non-functional, domain, inverse requirements, and design constraints. And then we had an in-depth discussion on requirements engineering processes and how these are related to software quality assurance. We talked about requirements defects. Requirements defects, as I have said today also, are typically defects that are omissions or defects categorized as errors in clarity and ambiguity. Then we discussed in detail problems that we face in documenting requirements. Then, coupled with these, we have problems in natural languages, because natural languages by their design are ambiguous. And so when we write requirements in them, we invite that ambiguity in the requirements documents also. And when we talked about guidelines for writing requirements, which I will share with you here today also, we said that we need to define standard templates for describing requirements, because that is going to take all the style and documentation issues away from us, and we should only focus on writing good quality, high quality requirements. We also said that we need to use language simply, consistently, and concisely. We do not need to use difficult phrases or words and phrases which mean multiple things, have multiple meanings. We should use simple words, simple sentences, and simple language should be applied, because that enables us to read it and mean it only once, giving one meaning. We should use diagrams appropriately to explain the text that is contained in the requirements document. We also said that we should use some notational languages. We need to supplement natural languages with other descriptions of requirements, and there are a number of technical languages available that help us in documenting requirements, and UML has become one of the standards. In the last few years, it has become the de facto standard for documenting requirements and designs. These documents, the UML notations are not replacements of requirements written in the English or any other natural language, but are used to supplement. And we should try to specify requirements quantitatively, especially for non-functional requirements, because we are trying to clarify the intent of the user. If we don't quantitatively write requirements, then they become goals, and it is difficult to prove goals. It is difficult to prove conformance when we are at the acceptance level. And so we should try to write quantitatively as accurately as possible the intent of the user. Some of the additional guidelines for writing requirements include: state only one requirement per statement, state requirements as active sentences, always use noun or definite pronoun when referring to a thing, do not use more than one conjunction when writing requirement statements. And so these are additional things, but our primary goals were the 6 that I outlined earlier. We should also try not to use weak words and phrases. Such words and phrases are generally imprecise and allow expansion or contraction of requirements beyond their intent. Some of the examples of the words to be avoided are about, adequate, and/or, appropriate, as applicable, if practical, when necessary. So you see that these words or phrases can have ambiguities built in them, and we should try to avoid using such words as much as possible. We should be as precise as possible and not invite additional ambiguity. We know that writing requirements which are not ambiguous, which are clear, which are complete, is itself a very difficult task. And if we try to use, and if we include words and phrases like these, then we are inviting trouble for ourselves. We also talked about requirements document. Users of the requirements documents. Users include system customers, managers, system engineers, test engineers, and people who are going to maintain the system, maintain the software system. And so we need to write those documents in such a way that the document itself is of high quality, and ultimately it results in the design which is of high quality. So what are the quality attributes of a requirement document? Without going into detail, I'll basically revisit them with you here so that you can go and read the material that you have on this topic. A requirement document should be correct, it should be unambiguous, it should be complete, it should be verifiable, it should be consistent, it should be understandable by the customer. Requirements document should be modifiable, it should be traced, traceable, and it should be design independent. A requirement document should be annotated, concise, and organized. These are the 13 quality attributes of requirements document that we have discussed in quite a bit of detail. After that, we talked about software design and quality assurance. Software design is very important because at this time we are entering into the solution space. We are making a transition from the problem space into the solution space. Design is the place in software engineering activities where quality needs to be fostered. Then we talked about design defects and the impact of design defects. We also talked about design model and design process. And with respect to both of them, that is design model and design process, we talked about guidelines and principles for developing a design model and following the design process. We also discussed in detail quality design concepts, and these concepts I will revisit with you without much discussion because of the time limitation. The first thing we talked about was abstraction. Abstraction permits one to concentrate on problem at some level of generalization without regard to irrelevant low-level details. Abstraction is one of the fundamental ways that we humans cope with complexity. And so abstraction is a very important design quality attribute. We must use abstraction in order to design high quality software products. Then we talked about refinement. A program is developed by successively refining levels of procedural detail. Refinement is actually a process of elaboration. We add things as we proceed further into the design process. And so we can say that abstraction and refinement are complementary steps. Then we talked about modularity, one of the oldest concepts in software design. Software is divided into separately named and addressable components, often called modules, that are integrated to satisfy problem requirements. And so modularity is the single attribute of software that allows a program to be intellectually manageable. We don't need to over-modularize because the problems of integration will overshadow the simplicity of the modules. And so we need to find a level of granularity where modules can be defined. After modularity, we talked about information hiding. Information hiding is again a fundamental principle. It means that the modules should be specified and designed so that the information contained within a module is inaccessible to other modules who do not have a need for such an information. Information hiding consists both of procedures, that is algorithms, and data. Information hiding is a very important design quality attribute. Then we talked about cohesion. Cohesion is the qualitative indication of the degree to which a module focuses on only one thing. In other words, we can say cohesion is a measure of the relative functional strength of a module. We can replace the word functional with data also. A cohesive module performs only one single task or is focused on only one thing. Highly cohesive modules are desirable, and there are a number of types of cohesion that we had talked about. As a last design quality attribute, we introduced and talked about coupling. Coupling is a qualitative indication of the degree to which a module is connected to other modules and to the outside world. In other words, we can say that coupling is a measure of interconnection among modules in software structure or software system. Loose coupling is desirable. Loose coupling is better. Simple connectivity is easier to understand and less prone to ripple effect that will happen if changes are introduced. And you know that changes will be introduced. And so this was our discussion on software design and quality assurance. We said and we agreed, and the community at large agrees, that we need to design the software with quality and focus. We need to practice those activities that encourage us to produce take us to high quality software design. If we do not put quality in the software design, if the process is not quality focused, I can assure you the design that you will create will not be of high quality. You need to pay attention to the design quality attributes that we have discussed. These are the backbone of any software design which has high quality in them. Take any product and you will find that these attributes are available fully in them. Then we spent a lecture talking about the role of programming and software quality assurance. Quality practices that we discussed in this course are these. We said using high-level programming languages is a good mechanism for quality assurance. We also discussed the importance of using integrated development environment. We also said that adopting standards, coding standards and other standards, prevent common types of defects. Common defects can be eliminated just by using different standards and conforming to them. And then we said prototyping, user interface and high-risk components is a very good practice, and it eliminates many risks. It identifies different possibilities which, if followed, will result in high-quality product. And we said that defining critical regions in software code is also a very good practice. It helps us in preventing deadlocks. Then we spent quite a bit of time on discussing reviews. What are reviews? A review is a meeting or a process in which a group of people are presented with a work product for the purpose of approval or finding defects. There are multiple kinds of work products that can be presented to a review, and there are different kinds of reviews. We talked about business reviews, we talked about technical reviews, we talked about management reviews, walkthroughs, and inspections. In a review, a team plays different roles. That is, members of the team play different roles. Then we talked about software inspections. and we talked about software inspections in several lectures. We introduced what software inspections are, why they are effective. With the help of published data and literature, I shared with you the importance of and effectiveness and efficiency of software inspections in finding software defects. And we spent quite a bit of time in discussing different activities that are performed in software inspection. What are those activities? Let's now briefly go over these inspection activities, and then we will talk about the roles that are played by team members. Software inspection process includes planning and scheduling. It includes overview. It includes preparation. Then we have the inspection meeting, an analysis meeting, rework, follow-up after the rework. Then we have prevention meetings, data recording and reports, and inspection process monitoring. Up till this point, we spent 3 lectures on discussing these activities that are part of the software inspection process. It is important to remember that we need to plan and schedule inspections so that the team members can participate. We need to have an overview meeting to provide any necessary background information on the material to be inspected. The preparation is an activity that is performed by the inspectors on their own so that they can get familiar with and identify major and minor defects in the work product. Then we have a collective activity known as the inspection meeting, followed by an analysis meeting, which is the first step in defect prevention. The rework is done to repair, in which the repairs are applied to all the defects agreed on in the inspection meeting. And if everything goes okay, then follow-up is done by the moderator and the producer, and the inspection comes to a close. The last 3 activities, including prevention meeting, data recording and reports, and inspection process monitoring, are not formally part of the inspection process, but they continue throughout. And are responsibility of the inspection coordinator. We had discussed each and every step in these activities, and we also talked about the roles of inspectors that include the moderator, the producer or author, the recorder, the reader, and the inspector. And in the last lecture, we talked about different practical issues related to software inspections and when they should be introduced in an organization, and what are the simple and comfortable ways in which these inspections can be practically introduced. In this lecture, I have gone over the material of 21 lectures. I have summarized the discussions that we have held in the last 21 lectures. And that is for you to help, for you to focus on the midterm. And then when we come after midterm, we'll talk about software testing. See you then.